Hey Kim, missed you all. Today we're doing a little bit of notes introducing this idea of percent composition. This is a little bit of math, but I promise it's not too hard, not too difficult. Percent is kind of something you guys should already know how to do. It's very, similar calculations. Really all you have to learn to do is like how to interpret the questions so that you know how to answer it. And from there, I think you guys will be pretty good. So it's not a terrible topic. So percent composition is used a lot in chemistry, especially in industry when people are developing things, medicine, CSI as well. It's used just to basically identify substances based on the percent by mass of an element that is in a compound, whether that compound is known or unknown. So it is something that is used a lot in chemistry, which is why we are kind of using it here. So for example, common compound table salt, sodium chloride, is always 39.3% sodium and 60.7% chlorine by mass. And we say by mass because we use mass to calculate this percent composition. If you just look at the formula NaCl, you would think that it's like a 50% composition of Na, 50% composition of Cl, because there's one of each per molecule. So yes, that's true. They're present in a 1-to-1 ratio, but those percents don't come from the number of atoms in a formula unit or molecule. It comes from the relative mass of each element in the overall compound. So we're kind of comparing the mass of the element in the compound versus the mass or the molar mass of that compound itself. So it doesn't matter how much you have of salt, whether it's a truckload, just a little sprinkle on your food, a cube, or even just one formula unit, think molecule of salt, it's always going to be 39.3% of that sample is sodium and 60.7 is chlorine. So here we have two different compounds that are both made of oxygen and iron. So we have iron 3 oxide and iron 2 oxide. So both are just made of iron and just made of oxygen, but they have different percent compositions. So if you look at these, they have different chemical formulas. So since the chemical formula is different, we do expect the percent composition to be different. Okay, so it looks like if you look at iron 3 oxide, we have 3 atoms of oxygen per formula unit, versus iron 2, we just have 1 per formula unit. So it would make sense that the percent by mass of oxygen, if we have more oxygen molecules, atoms in one molecule in one compound than we do of another, we would expect that percent by mass to be larger. So that is why the percent of oxygen by mass of oxygen in iron 3 oxide is greater than iron 2 oxide. We have 2 atoms of oxygen in every molecule versus just 1 oxygen atom in every molecule. So if we have more, that's going to mean more mass to that molecule overall, make up a greater percentage of the mass of that molecule. So to find the percent of anything, it's always just going to be the part that you're interested in divided by the whole of that sample. So for example, for your grades that you get on assignments in all of your classes, to find your percent, all that you do is you take the points that you earned for correct answers or completion, that's the part you're interested in, and divide it by the total number of points possible to be earned in that assignment, which is known as the whole of the sample. Percent by mass is very similar, same idea. We take the mass of an element we want to know the percent of, that's the part we're interested in, and divide it by the total mass of the sample, the whole of the sample. And there's 2 kind of ways that you could be given this. You could be told how many grams of oxygen you have in X grams of a sample, or you could relate this to molar mass. So molar mass is going to be used in here. You can also, through that, calculate the number of atoms that are in a sample as well. So those conversions that we did last chapter aren't going away. I'm just going to warn you now. That's something we're going to be using pretty much throughout the rest of the year. So again, what you're interested in divided by the whole, and you do want to make sure that the units are the same for your part and whole. So both in grams, both in kilograms, both in grams per mole, whatever. You want to make sure that your units are both the same. That way they cancel out to give you a nice percent, because percents don't really have a unit behind them. So here's just kind of a visual of how to calculate percent composition. You take the part over the whole and multiply by 100% to get it as a percent. Okay. You can also, you may know that, you can go from a percent to a decimal. So 50% is 0.5 and things like that. So that's where that 100 comes in. So again, here's the equation we'll be using for percent composition. The mass of an element divided by total mass. Again, it might be a mass that's given in the problem, or we might be relating it to molar mass, because either way, based on ratios, that percent composition should be the same. So if we look at the table salt example we looked at before, to find that 39.3% of sodium, we take the molar mass of sodium, 22.99 grams, and divide by 58.44 grams, multiply by 100, and we get 39.3%. Same thing with chlorine. We're taking 35.45 grams, dividing by this 58.44, multiplying by 100, and we're getting 60.7%. So where did this number come from? This is, again, the total mass. For this example, it's the total molar mass of the compound. So how do we find the molar mass of NaCl? All that we have to do is add together the molar mass of sodium and the molar mass of chlorine, which comes out to be about 58.44 grams. Okay, so that is where your denominator comes from. Your numerator can come, again, straight from the periodic table through molar mass. So for a practice problem here, we have what's the percent composition of calcium carbonate, CaCO3. So for this, we're going to find the percent of all elements in calcium carbonate. So the first step, we want to find that total molar mass of the entire compound. This question doesn't tell us that we have, 8 grams of calcium in a 38-gram sample of calcium chloride or anything like that. So we are just going to be using molar masses here. So first we want to find the total molar mass of the compound. To do that, I'm taking 1 times the molar mass of calcium, because we only have 1 calcium, plus 1 times the molar mass of carbon, because there's only 1 carbon, plus 3 times the molar mass of oxygen, which, because we have a little subscript 3 here for oxygen. And that comes out to be about 100.09 grams per mole. So that is the molar mass of the entire compound. So when we plug into this equation here, that molar mass is going to be in the denominator here, the total mass. So for calcium, we're taking 40.08 grams, dividing by our total mass of 100.09, multiplying by 100 to get 40.04%. For carbon, almost the same calculation, but this time we're taking the molar mass of carbon in the numerator, 12.01 times 100%, and we get about 12% carbon. For oxygen, we have something a little bit different in the numerator. So here I wrote it out to be 3 times 16, because remember, there are 3 atoms of oxygen for every molecule of calcium carbonate. So I have to multiply the molar mass by 3 to account for all of those oxygens. So from here on out, I won't break it down into that 3 times. I would just put what 3 times 16 is, which is about, let's see, times 2 is 32, 48. So it would be 48 grams over 100.09 grams. And again, multiply by 100, we would get 47.96% of oxygen. So this is what calcium carbonate is made up into based on the percent composition. Another practice problem, we want to know the percent composition of potassium permanganate, which is KMnO4. So it's very similar to the last problem. Move that over. First step, we want to find the molar mass of the compound. So here we're going to have 1 times the molar mass of potassium plus 1 times the molar mass of permanganate, and then plus 4 times the molar mass of oxygen, again because we have that low 4 subscript. So our total molar mass for this compound is 158.04 grams per mole. For potassium, we're taking the molar mass of potassium, 39.1, dividing by 158.04, multiplying by 100 to get our percent, and we get 24.74% of potassium. For manganese, it's very similar. 1 times 54.94 gives us 54.94, divided by 158.04 times 100 to get 34.76% of manganese. And then for oxygen, we have 4 times 16, giving us 64 grams for the numerator, divided by the total molar mass of 158.04, and we get 40.5% oxygen. So for this problem, we want to know what is the percent just of nitrogen in sodium nitrate. So this is NaNO3. So instead of doing the percent compositions for all of these elements, we can go ahead and just focus on nitrogen rather than waste our time doing calculations we don't need. So go ahead, pause the video, and see if you can calculate the percent nitrogen in NaNO3. So first, hopefully you found the total molar mass of the compound. So we're going to have 1 times the molar mass of sodium plus 1 times the molar mass of nitrogen plus 3 times the molar mass of oxygen. And that should give you about 85 grams per mole. If you got somewhere near there, that's great. Could just be different rounding, different periodic table. I know I use a different periodic table than ptable.com, but if you're using ptable.com, you probably got a little bit different answer, which is fine. The next step, we're taking the molar mass of nitrogen, 14.01, and dividing it by the total molar mass of the compound and multiplying by 100%. So you should get 16.48% nitrogen. This is a problem that's worded a little bit differently. So this is a situation where we are given a weight of oxygen and iron, and we are asked to find the percent composition of that sample that way. So this time, rather than finding the molar mass and using the molar mass of the elements, since we don't have a chemical formula, we are using these values that they provide in the question. Now later on, we will be able to use percent composition and information like this to actually figure out what the chemical formula of the compound that we essentially analyzed is. So we could work backwards to find the chemical formula, and we will get into that later. So for this, we are taking finding the percent of iron by taking the known amount of iron we have, 28 grams, and dividing by the total mass, which is 36 grams. So if you take 28 plus 8, you get 36 grams. We're multiplying that by 100, and we find out that this sample is 77.78% iron. Oxygen, very similar. This time we're having 8 grams divided by 36 times 100 to give us 22.22% of oxygen. Now, something you should notice about all these percents, and maybe you've caught on, is that they always add to 100%. So if you want to go back and check your work after each problem to make sure that you did it correctly, or to feel good about your answer, just go back and look. Do your percentages add up to 100%? Or even 99.99 is usually a good indicator. That's a good way to check your work. So the fact that these do add up tells me that yes, I did my work correctly. That's good. If I had something like, I'm going to go back to this one. If I've added these up and I didn't get 100%, the first thing I would probably look at is my calculation for the percent of oxygen. So maybe instead of putting 64 in the numerator down here, I put 16. I forgot to multiply it by 4. So that's a good way to check your work here. If something's off, usually I first check the elements that I have multiple of and make sure that I actually did that calculation correctly.